Now you're ready to go home and read a shampoo, aren't you? Anybody do that ever the last couple of days? Anybody look at the shampoo bottle the last 2 days? What'd you think of it? A little bit daunting still, huh? Still, but now you know what all the numbers and stuff mean and the names, right? Did you see some of that on there? Some of the numbering and stuff? Sometimes. No, not really. Some of them have them and some of them don't. Some of them, what they do is, instead of using like these long names, they just give it a common name, like lauric acid or something, instead of using the whole name. Because the whole name is scary. All right. Now we're going to talk about a different kind of isomer. Remember we said the other day, single bonds are free to rotate like the wheels on a car, like on a Hot Wheels car. Single bonds are like the axis. Well, when you have a double bond, because of the way that the electrons work, they're not capable of rotating. Double bonds cannot rotate. So what happens is you create what are called cis and trans isomers. Okay? Think about my thumbs being hydrogen atoms. When they're on the same side, these are cis isomers. When I turn it upside down like that and they look like this is a trans isomer. We're going to do some examples, okay? They have the same molecular formula. They even look a lot alike, except that this double bond is rotated 90 degrees. And we're going to show that. Or 180 degrees. Okay. This example down here. Let's draw a line through the middle of these molecules. Look at where the hydrogens are. Are they on the same side? So both of these two molecules are 1,2-dichloroethene. But when I expand it out and draw the whole structure, look down here. These hydrogens are on the same side, so this is cis 1,2-dichloroethene. Here they're on opposite sides, right? So this is trans 1,2-dichloroethene. And I know y'all are going, who really cares if they're on the same side or opposite sides, right? Well, guess what? Your body cares. We're now starting to see how, think about these two things. What if these two things were a key and you're trying to put it into a lock? Do you think both of those would work in the same lock? Yeah. Look at the shape of them. They're way different, aren't they? So, anybody know anything about lock and key mechanism? This is how enzymes work, right, in your body. They bind with particular molecules based upon the shape of that molecule. If the molecule's not the right shape, we don't bind. Cis and trans isomers are extremely important in determining shapes. Okay? And let's look at another example. This is the simplest molecule that can have cis and trans, and I'm going to show you why. So this is 2-butene. Let's look at 1-butene. I'm going to go back one. Sometimes double bonds do not have cis and trans isomers. Oh, my goodness, my drawings are terrible. This molecule cannot have cis and trans isomers. Here's why. Look at this carbon right here. The two hydrogens on here. In order for it to have cis and trans isomers, what's here and here has to be different on both carbons. Now this one has this and this, right? So this is different, but this side, both of these things are the same. So it can't have cis and trans isomers. So the two carbons on either side of a double bond both have to have two different things bonded to them, okay? And we'll show that here. So this is one butene. Can't have cis and trans because this has two hydrogens. But look here, two butene. Rule 1, this is different than this, and this is different than this. So it can have cis and trans isomers. These are on the same side. So this is cis 2-butene. Down here, the hydrogens are on opposite sides. So this is trans 2-butene. Okay? Cis 2-butene and trans 2-butene. Fair enough? Cis means same side, trans means opposite sides.
So on the 2-butene up there at the top,
Yeah.
you said those two bonds are different?
No, what I'm saying is this is different than this, and this is different than this, right? On each carbon on the double bond has two different things bonded to it. What I showed in 1-butene is look over here. This and this are not different.
Oh.
So it can't have cis and trans isomers. But for this one, both carbons have two different things bonded to them. So this does have cis and trans.
Okay. I was looking at it.
Yeah. Now, they have this pretty picture of this big moth on here. And they say that pheromones are produced by lots of organisms produce pheromones, right? They can do lots of different jobs. They can warn of danger, they can mark a trail, or the most important one, attract a mate, right? Now here is the molecule that this particular moth makes. It's a silkworm moth, and it has two double bonds in it. Look at it. One of these is a cis isomer, and the other is a trans isomer. I want you to look at them and decide which is which. Ready? This one right here is what kind? This one's trans, right? Because look, hydrogens are opposite. That means this one must be what? Cis, because they're on the same side of the molecule, right? So you say, why is this important? It has to do with how they fit into different structures, okay? These double bonds create, these cis and trans isomers create kinks that do not rotate in this molecule. So, i.e., fats have lots of double bonds in them. What do you have at room temperature? What's a fat at room temperature? Is it a solid or liquid? Fats are what at room temperature? They're solids, right? Butter is a solid, isn't it? And it's a fat. What about oils? Oils tend to be liquids, like vegetable oil is a liquid at room temperature. Why are vegetable oils liquids and fats are solids? Because oils contain lots of double bonds, okay? So that the molecules are all like crooked and bent and they don't fit together very well. Versus fats, they don't have a whole lot of double bonds, and so they just kind of lay on top of each other and they kind of are attracted to each other. And that's why cis and trans is important for some of this stuff, okay? And we're going to talk about lipids if we get there. I don't like the way these are drawn. I would put a hydrogen down here, right? This is cis 1,2-dibromoethene, and this is trans 1,2-dibromoethene. They just kind of rotate it a little bit. Yes, ma'am?
Can you number that? Can you show me how you number that? How are you getting the, I know how you're getting the numbers, but can you show me? Okay. So, okay.
There's only two carbons, right?
Yeah.
Ethene means two carbons. And in this case, it's symmetrical. It wouldn't matter if you numbered it 1, 2, which direction you go.